This is part 7 in a series of videos in which I'm attempting to repair an HP9830A desktop calculator. In the previous video we traced a potential fault to this card. This is one of the CPU cards and it's the microcode generator. And what seemed to be happening is that following a reset, we were indeed resetting to the correct address. The data coming out of the ROMs was correct. However, the following address, that's the next address, was incorrect. And it appeared that bit 0 was a 1 when it should have been a 0. And that turned out to be because the BRC signal is stuck high. Now the BRC signal is derived directly from one of the ROMs on this card. So looking at this ROM appeared to be the next step. So that's what I'm doing. I've got this hooked up to the logic analyzer. I'm looking at the 4 data bits coming out of it. So I'll point the camera at the logic analyzer, we'll capture some data and see if this looks correct. Okay, so looking at the logic analyzer screen, you can see that not only do I have the BRC signal, but I also have what I've called data, and data is the 4 bits that is coming out of the ROM that I suspect may be faulty. So it's these 4 bits here, including the BRC output. So I'll power up the machine and we'll capture some data and see what we get. So I've powered up the machine. The data, as you can see, is reading F at this point. So I'll just compress this a bit. And if we go across, we can see that the data is always reading F irrespective of the address. So the address going into the ROM is the blue trace. So you can see here that whether it's FE, A7, FF, then the output on those 4 data bits is always F. So they're always high. Okay, I've obtained a copy of the disassembly listing for the microcode ROMs, and if we look at address 255, that's FF, and follow it across, then the 3rd column from the right is the data we should be getting out of the ROM we're looking at. This is ROM 7, and as you can see it should be a value of 7, and it's not, it's shown as F, and the same is true if we go all the way across. Now at this point we could hook the analyzer to the other ROMs and check those at the same time, but the problem is of course that because we're not supplying the correct address to the ROM in the first place, then it would be easier to fix this first ROM and then examine the other 6 ROMs and see if they're giving out the correct data. So far I've only been able to check a few addresses, as you can see, but at all the addresses, so that's 5A, A7, FE and FF, we're getting F coming out of the ROM, and none of those addresses should give out an F, so it looks fairly certain that particular ROM is not working. So what I'll do now is take the ROM out of the board. We'll attempt to read it, and if we can confirm it's faulty, all well and good, but I'll replace it anyway, and hopefully the code that I have is correct, and then we'll get the board reinstalled, get the analyzer back on and see if things have improved at all. Okay, so I've got the ROM chip out of the board. I've managed to do it without damaging either the chip or the board, although it's surprisingly difficult to get these ICs out of this particular board. The solder seems to have completely dried up and it just will not flow, so getting these out, or getting this out was quite tricky, but I've got it out. So what I'll do now is take it over to the programmer and try to read it and see if it really is dead, and go from there. I've got the ROM plugged into the programmer. I'll try to read it, see what happens. Surprisingly it's read without any errors. Let's have a look at the data. So it's just the first 256 nibbles that we're looking at, or 256 bytes. The high nibble of the byte is masked off for this particular device. and surprisingly the data appears to be correct. I wasn't really expecting that, but the ROM appears to be working. I'll try and read it again, see if it's reliable. And it's read successfully again. And what I'm looking at here is the bytes that I have compared against the disassembly listing, which should start as 779F73, and as you can see that is correct, and the rest looks normal. There's no weird kind of patterns or anything that you normally get when ROMs fail. So that's quite a surprise. I need to go back now to the board and see if we're still getting the same effect, and possibly what's pulling those lines high. Okay, well this got a bit strange. I put the chip back into the board after testing it in the programmer, and I got the same results. It was still outputting the wrong data. So what I did is I programmed one of the alternate chip types that I mentioned in the previous video, and I put that in, and I'm now getting different results. I think this is partially failing, and the loading on the programmer is not the same as on the actual card. I'm looking at it very closely. I don't know if this will come out on camera, but pin 1, or connection to pin 1, you can see these grey traces. These are conductive traces. Seems to be damaged where it's going to pin 1, so I think it's just only a partial connection there. But either way, it works in the programmer but not in the card. But I have taken an image of it, so I do at least have what I believe is the correct binary file to put into this device. Having said I got different results, it's still not doing what it should. So I'll demonstrate that. I'll connect the analyzer to this particular ROM chip. I'll reposition the camera so you can see the analyzer screen, and I'll do a new capture and show you what the problem is now. Okay, so we're looking back at the analyzer screen. I've got the same connections I had before, where we're looking at the address going into the ROM chip and the data coming out of the ROM chip, along with the BRC and the multiplexer output. So I'll arm the analyzer and turn on the HP. We've now captured some data, but now you can see it is different. The initial addresses are the same, but we're now getting the correct data out of the ROM chip. If I scroll across, we can see that we are getting different data coming out of the ROM chip, and it does appear to be correct for the addresses that we're looking at. The BRC line is also now low, which is what we would expect. That's driven by bit 3 of the data line. So as you can see, it's got a value of 7, so the bottom 3 bits are 1, the third bit is a 0, and that's the BRC line, so that's now correct. So we're now getting the correct data at this point anyway out of the ROM. However, we're still getting the wrong value showing here, and if I scroll across, you can see that we're still jumping to A7 rather than A6. So we'll have a quick look at the schematic. So what we appear to be getting now is BRC is correct. There's a high level here, but it's getting through this gate, and it shouldn't be. BRC is low, and we're not getting the data being fed through here, so there's something wrong in this circuit somewhere. So what I'll do is I'll get the scope and we'll look at these points. So we'll look at this first gate and the second gate and see what these are actually doing. I'll reposition the camera, I'll turn the analyzer off because it's a bit noisy, and we'll see what's going on with those logic gates. Hopefully you can see the scope screen okay. So what I'm going to do is look at the two inputs to this first gate. So that would be the BRC line, which should be low, and then we'll just see what's coming out of the multiplexer. Okay, so we'll look at pin 1. This is the output of the multiplexer, and you can see that's high. Pin 2 is BRC, and that's switching as it should. We'll look at pin 3, which is the output of that AND gate. and obviously that's wrong. So it looks like that gate may be faulty. So the point we're looking at here is this output, and it's not giving us the correct value. We'll look at this to see if this gate's working. So that's pin 9 of IC1, which I believe is that, and yes, that's the same. The output of that gate is low, as it should be, considering the input it's getting. So this point here is low, so this should be disabled, which explains why we're not getting anything coming through here. So we'll look at this gate. So pin 4, and that's correct, the output of the inverter. Pin 5 is the value coming from the ROM, so this is the bit we're trying to XOR into the address, and that looks correct. And then the output of that gate is again incorrect. So the outputs of both of these gates are not doing what we would expect. So it looks like, and this is the same chip, so it looks like this chip is now faulty. That could be what damaged the ROM. So I'll swap that chip and then get back on camera and see if that improves things. Okay, I've replaced that chip, and sure enough it tests faulty. It's a 7408. I've replaced it with a 74LS08. So what we'll do now is look at the signals on the scope, see if they now look as they should. So looking at the same points, we'll check pin 3 first and see if that's switching the way it should be. And if you remember before, it was just kind of stuck halfway. As you can see on the scope, that's now switching the way it should. And then the output of the other gate on the same IC was also kind of stuck halfway. That's pin 6. So we'll look at that. And again, that's now switching as it should. So we'll look back at the logic analyzer and see if we've improved things at all, and if the microcode can get any further than it did last time. Okay, so we're looking back at the analyzer screen. I have the trigger set to FE, and if I power up the HP, we'll see if we can capture something. And indeed we have. We have the reset vector, as we'd expect. The address modifier is 01, as it should be. We then jump to FE, and the address modifier given at that address is 58, but notice this time it's not changing to 59, which is correct. If I scroll across, you notice there are 16 clock cycles for these instructions, which again is quite promising. It means that the divider on the clock board is being correctly loaded with the value in the instruction. Notice the 58 is correct all the way up to the end of the instruction. The date is reading 0 simply because I have the board plugged fully into the machine, so I can't attach that clip to the ROM, so we're not reading the actual data coming out of the ROM anymore. So we go from FE, we jump to A6 as we should. Quite what happens after that, or is supposed to happen after that, I'm not quite sure. We can see there is some activity going on. So what I'll do for the next video is start tracing through the code. I'll put the remaining boards in, and we see how far we get and what the next fault is.